So we're going to take a couple minutes here and kind of differentiate the kinds of pathways that are operational when we talk about exogenous protein sort of breakdown and then endogenous protein breakdown. So specifically, exogenous refers to proteins that we eat. So we had to spend a lot of time in our lipid learning unit sort of talking about the digestive process and importantly the uptake from the GI tract and then importantly the transport of those hydrophobic molecules. We're going to not need to talk as much about the transport piece here, but it is important to talk about sort of that digestion piece and importantly sort of this exit out of the GI tract. So when we're talking about exogenous here, we're talking about proteins that we eat. So dietary proteins. And so just a few pieces to sort of think about. We talk about what we encounter with proteins in the stomach is they're going to encounter a protein called pepsin. Okay, so pepsin is going to start sort of hydrolyzing those peptide bonds. Remember, we're having hydrolysis of those peptide bonds, and so pepsin must be an enzyme that has a pH optimum that's much lower than most enzymes in our body because it's going to be operating in that low pH of the stomach. Then we're going to have some of these degraded peptides make their way to the small intestine. And there they're going to encounter serine proteases. And hopefully you remember serine proteases are made in the pancreas. So the pancreas has both exocrine and endocrine function. So just a little review, neat organ that does so much in our body but kind of is buried and doesn't get a lot of press, if you will. But exocrine function are things that are produced by an organ that are excreted into the external environment. So because the gut tube is an external environment, that's an exocrine function, is making those important digestive enzymes. Endocrine functions, we've also talked about of the pancreas, are things like the production of insulin and glucagon, right? Because those are going to be hormonal signals that are secreted into the bloodstream that allow us to sort of regulate many metabolic processes. So we've finished sort of breaking down these proteins into peptides into free amino acids. And the key here, the theme that we've talked about is the importance of uptake of monomers out of the GI tract. So the uptake of monomers, and specifically here, we're going to be talking about amino acids. When it was carbohydrates, it was talking about monosaccharides. When it was triglycerides, triglycerides do not come out of the GI tract. We need to break them down into free fatty acids, or you can have monoacylglycerides or even diacylglycerides. You just cannot have three fatty acids appended onto a glycerol backbone and get those out of the GI tract. But that uptake of monomers is an absolute sort of requirement, a theme that we're going to see, and sort of a piece that we've talked about a lot as a thread throughout the course is the importance of the integrity of that GI membrane. Remember that your GI membrane is one cell thick. So your tube within a tube is one cell thick. One cell separates you from the inside and outside environment. So the inside of the entirety of your body is separated from the outside environment in your gut tube by one cell. Now, of course, there's a nice, thick layer of mucus and all kinds of other things that are important in terms of sort of the environment that we have there, but one cell thick, and we only let monomers get out of that. And that's really important because we need to maintain that integrity. So highlighting that we're going to have only amino acids, change color here, we're only going to have amino acids, monosaccharides, and we're going to have either fatty acids, free fatty acids, monoacylglycerides, or diacylglycerides that are going to be able to get out. And the counter side of this, if we don't have integrity, right? If that integrity is faulting, so if our integrity is failing, that's when we have leaky gut. And years ago, this was sort of like a fanciful sort of, theory that there wasn't a lot of evidence to support, but there is a lot of evidence to support the importance of the integrity of the junction between these single cells to make sure that only monomers get out. And particularly related to this learning unit is if we have not amino acids get out, but if we have peptides get out into the bloodstream, that can cause inflammation, and it can also cause an immune response that can ultimately down the road be problematic. So again, if we've got leaky gut, part of the problem that can happen is we can have peptides enter the bloodstream. And when you have those peptides enter the bloodstream, that's where you basically can have an immune response. And again, that immune response can lead to inflammation. And related to that immune response, we've talked about this concept of molecular mimicry. Right? So if you've got this little peptide that comes in and your immune system kind of, gets a go at it and says, this doesn't look right, this looks foreign, it's going to develop antibodies for that. Now, if this little piece of protein looks similar to other proteins that are normal, healthy U proteins in your body, you will develop an autoimmune disease. So if this looks like a little piece of your thyroid, you're going to have attack of your thyroid. You're going to develop Hashimoto's thyroiditis. If this looks like a little piece of your pancreas, your beta cells of your pancreas, you're going to attack those. Your beta cells are going to get destroyed. You're going to develop type 1 diabetes. Okay, so whatever this sort of resembles, it can start developing an autoimmune disease. So that's why it's really important to maintain that gut integrity. Okay, so that's the exogenous arm. Let's spend a minute and talk about the endogenous arm. How do we sort of break down proteins once they're already in our body? We're not talking about digestion and sort of getting them into our bloodstream. I'm going to break this into two sort of stories and two sort of arms. I'm going to talk about non-specific degradation and specific degradation. So non-specific and specific. Okay, so when I'm talking about non-specific degradation, I'm talking about lysosomal degradation. So using the lysosome, right, that we've talked about, the lysosome is one of those organelles that you'll find in eukaryotic cells. So it's a little compartmentalized piece that contains enzymes, and importantly, enzymes that operate at a high pH. So it's going to be high pH, and then we're going to have enzymes that we have within that lysosomal particle. When we talked about receptor-mediated endocytosis, remember we talked about fusion of that receptor-mediated particle, first fused with an endosome, low pH to sort of disassociate sort of pieces from that, and then we fused with a lysosome to increase pH and sort of digest everything that's there. That's why the lysosome is often called the stomach of the cell. So make sure you don't get confused when it says stomach of the cell and think that it has a low pH. It has a high pH, but it's called the stomach of the cell because it basically degrades and digests and breaks down a lot of important proteins that we might have that need to be degraded. Okay? So highlighting, this is not something that's going to be happening in a time of plenty. In general, lysosome degradation is going to be happening in a time of need, okay? So this is not happening under a time of plenty. Sort of, this is a time of need sort of situation. So a time of need. And as we'll see, maybe it's a need for this tissue to be degraded, but it also might be the need to break down that tissue for sort of building blocks, okay? So again, in this time of need sort of situation, we are going to have the liver and the kidney. We talked about them being able to selectively atrophy. And one of the reasons that they're able to selectively atrophy is they have an important tag. And we call this the KFERQ tag. And I don't need you to remember that that's what the tag is, but if we think about what those amino acids are, we've got some kind of rare amino acids. We've got lysine, we've got phenylalanine, aspartic acid, arginine, and glutamine, right? Amino acids with functional groups that we don't see sprinkled frequently all over proteins. So having them all together is kind of an important way to signal that, hey, this is a protein that can be targeted and broken down by lysosomes. Okay, so why am I calling this non-specific degradation? Well, you basically just throw it in the trash compactor and it's non-specific hydrolysis by these enzymes. Okay, so these enzymes are just going to be chewing everything up. So another time of need, so again, we should say that this is again during a fasting sort of situation that we might need to be sort of breaking this down. Again, a time of need might be what we see with uterine degradation. And I mentioned this already in kind of a previous slide, but you have at birth, you have about a 2-kilogram tissue or organ muscle that you have there. And about 10 days after birth, this is about 50 grams. So a significant sort of breakdown in the size of this large muscular organ. Okay, so another piece to sort of highlight is lysosomal degradation is really important, okay, but it can be faulty. And when something is faulty, it can lead to a disease state. So a prevailing theory about one of the causes of the symptoms of rheumatoid arthritis. So rheumatoid arthritis is an autoimmune disease. It's where your body attacks your joints. That's different from osteoarthritis. Osteoarthritis is literally inflammation that happens when you have rubbing together. This happens as people get older. As you lose your cartilage, you can have bone rubbing against bone, and that can lead to inflammation of your joints. Rheumatoid arthritis happens when you have an immune system response and you have an attack of your joints. Well, one of the things that's thought to be sort of playing into this is a faulty sort of release of lysosomes into that extracellular space. So as you release those lysosomal contents and they start to literally be digesting stuff that's in your joints, that can lead to inflammation. So hypothesis is, again, the connection between lysosomes and rheumatoid arthritis. So lysosomes are released into joints with rheumatoid arthritis. So that's what RA is rheumatoid arthritis. Okay, so I'm calling this non-specific degradation because you basically just throw proteins into this organelle that has a high pH and pH adjusted enzymes that are just going to, hydrolyze those peptide bonds, break those proteins down into their component amino acids. So when I talk about specific degradation, I'm going to be talking about the proteasome. And this is basically a protein degrading machine that is going to degrade proteins that are tagged. Okay, so this is a machine that breaks down tagged proteins. So a really neat sort of macromolecular structure. It's a protein itself that if you get tagged with what's called sort of a death tag, this tag that we have here is called ubiquitin. Okay, and it's often referred to as a death tag. Well, if you are a protein that gets a ubiquitin slapped on it, that's basically means that you are going to be trafficked to the proteasome to kind of be pulled inside. And again, this is a protein machine that selectively breaks down proteins that are tagged with ubiquitin. Okay, so talking about some of the proteins that would be sort of broken down here, we're going to see proteins that are called pest proteins. And a lot of these proteins have acronyms that refer to amino acids that are present in high concentration. So we've got proline, aspartic acid, serine, threonine. Again, functional group laden amino acids. We don't see those kind of sprinkled in high concentration because they usually are doing important biochemistry. Remember, the bulk of what we see with proteins are what make that hydrophobic core so that we can have proteins kind of collapse and have that greasy interior, and then we've got functional groups that are put there to label the protein enzyme to do its biochemistry. Okay, so pest proteins are going to be things that are frequently tagged with ubiquitin. Importantly, what we see on the N-terminus, so the N-terminal tag is important to determine how quickly something might be tagged with ubiquitin. So as an example, if you see something that might have, let's see, DRLKF, and One of the things that you should be doing for yourself right now is literally throwing out alphabet soup and see how quickly you can say what the amino acids are and make sure that importantly you know what functional groups are there. So we're going to see a laundry list here of amino acids that tend to have functional groups. We've got aspartic acid, arginine. This is a weird one. It's not a functional group laden one, but leucine, and then lysine and phenylalanine. Okay. If you have this as your tag, so again, if you have that as your N-terminus on your tag, your T1/2, your half-life, how long you stick around, is only going to be 2 to 3 minutes. So these are going to be short-lived proteins in your body. They're not going to stick around for very long. Contrast that now with a tag that is AGM-STV. So clearly I'm reading, I don't even remember what these are, but you should be able to look at these and say that's alanine, glycine, methionine, serine, threonine, valine. So with the exceptions of the serine and threonine, we see a lot of sort of hydrophobic amino acids that are there. But if that's what's on our N-terminus, this is going to be something, so again, this is a different tag that we'll see. This will be something that means you have a half-life of 10 or more hours. So proteins that are going to stick around for a long time are going to have a very different N-terminal tag. So one of the things, again, we're going to see is that depending on what amino acids we sort of have there, we're going to sort of target them for degradation. And degradation can be in a specific sense through something called the proteasome, once we tag them with ubiquitin, or in a non-specific way, we can have things get trafficked for fusion with a lysosome that's going to facilitate their degradation in that way.